Welcome to Delta Wave History. Tonight, we explore the ingenious medieval method for cooling buildings without any electrical power. Wind whistles through hollowed brick towers, pulling scorching air upward to leave the stone floors beneath breathlessly cold. We will examine how ancient architects harnessed thermal mass and pressure differentials to drop temperatures by 20 degrees. This passive ventilation system proves that sophisticated climate control requires only clever geometry and a steady breeze. As you settle into your bed, allow your mind to step back in time to a sun-baked desert landscape. The daytime temperatures here easily exceed 100 degrees, creating a shimmering haze over the arid ground. Yet inside the clay and mud brick structures, the inhabitants rest in comfortable, shaded tranquility. To understand how this is possible, we must look at the specific materials used by medieval builders. The foundation of this passive cooling begins with the earth itself, specifically a mixture of clay, sand, water, and straw. When these elements are combined and baked in the sun, they form a material with an exceptionally high thermal mass. Thermal mass refers to the ability of a material to absorb, store, and eventually release significant amounts of heat. During the long, blistering days, the thick adobe walls slowly absorb the relentless thermal energy from the sun. Because the walls are incredibly thick, often exceeding 2 feet in depth, the heat takes hours to penetrate to the interior. This intentional delay is known as thermal lag, and it forms the first crucial step in our medieval cooling process. By the time the absorbed heat finally reaches the inner surface of the walls, the sun has already begun to set. The night air in the desert drops rapidly, becoming crisp and cool. It is at this point that the thick walls begin to release their stored heat back into the cooling night sky, rather than into the living spaces. But thermal mass alone is not enough to maintain a truly cold environment during the peak of summer. For that, the architects needed to capture the wind, leading to the invention of the wind catcher, or baggia. Imagine a tall, square tower rising high above the flat roofs of the desert city. The tower is divided vertically into multiple internal shafts, facing the cardinal directions to catch the breeze, no matter which way it blows. Higher above the ground, the air is naturally cooler and moves with greater velocity than the stagnant air at street level. As the prevailing wind strikes the open vertical slats of the wind catcher, it is forced downward into the shaft. The geometry of the slats is precisely angled to funnel the maximum volume of air down into the building below. As this air descends through the dark, shadowed masonry of the tower, it begins to cool even further. The bricks lining the interior of the shaft have been cooled throughout the previous night, and they now draw heat out of the descending air. This creates a continuous downdraft, bringing a steady, refreshing breeze directly into the central living quarters. However, the medieval engineers did not stop there. They integrated this airflow with another brilliant system. Beneath the buildings, deep underground, lay a network of subterranean aqueducts known as qanats. These qanats carried cold meltwater from distant mountains, flowing silently beneath the desert floor. The architects aligned the wind catcher's downdraft so that the incoming air would pass directly over the surface of this underground water. As the dry desert air moves over the cold, dark water, a phase change occurs. The water absorbs thermal energy from the air to evaporate, which significantly lowers the temperature of the air itself. This process, known as evaporative cooling, functions exactly like a modern swamp cooler, but entirely without electricity. The freshly chilled, slightly humidified air is then drawn up into the main living spaces of the house. This newly conditioned air displaces the warmer, stale air that has accumulated in the rooms. Here, we encounter the beautiful physics of pressure differentials and the buoyancy of air. Warm air is naturally less dense than cold air, causing it to rise toward the ceiling. At the top of the room, on the opposite side of the incoming cool breeze, a secondary shaft, or the leeward side of the wind catcher, serves as an exhaust. The wind blowing past the top of the tower creates an area of low pressure on the leeward side. According to the Bernoulli principle, this fast-moving air exerts less pressure, creating a vacuum effect. This vacuum actively sucks the rising warm air out of the building, venting it back into the atmosphere. It is a seamless, silent engine of cooling, driven only by the natural forces of the earth and sky. The continuous cycle of cool air entering, heavy with moisture, and warm air exiting creates a microclimate of peace and comfort. The occupants of the building can sit on carpets laid over cool stone floors, listening to the gentle hum of the airflow. The architecture requires no maintenance, no moving parts, and no fuel. It simply stands, a monument to human ingenuity, patiently waiting for the wind to blow. Let us delve deeper into the specific properties of the mud brick itself, a substance known as adobe. Adobe is created from a highly specific ratio of sand, silt, and clay, mixed with water and a fibrous organic material, typically straw. The sand provides the structural integrity, acting as the microscopic skeleton of the brick. The clay acts as the binder, filling the voids between the sand particles and holding them together when dry. The straw is perhaps the most crucial element for longevity, as it provides tensile strength. Without straw, the mud brick would easily crack and crumble under the intense thermal expansion and contraction caused by the desert sun. The mixing process is laborious and repetitive, traditionally done by treading the wet mud with bare feet until a uniform consistency is achieved. Once mixed, the heavy sludge is pressed into wooden frames, forming identical rectangular blocks. These blocks are then laid out in the sun to cure, a process that can take several weeks depending on the humidity. During this curing phase, the water slowly evaporates, leaving behind a dense, solid mass with remarkable thermal properties. The specific heat capacity of dried adobe is approximately 1 kilojoule per kilogram per degree Celsius. This means it takes a substantial amount of energy to raise the temperature of a single brick by even 1 degree. When thousands of these bricks are stacked to form a wall, the total thermal mass becomes immense. The mortar used to bind these bricks is often a slurry of the exact same mud mixture, ensuring that the wall behaves as a single, continuous thermal unit. We can observe the careful masonry of the tower, where each brick is laid with mathematical precision. The joints are kept incredibly tight to prevent any unwanted air leakage, which would disrupt the carefully engineered pressure differentials. Some wind catchers feature internal wooden crossbeams, serving both as scaffolding and as tension rods to stabilize the tall structure. Even these wooden beams play a role in the cooling process, as they are porous and hold slight amounts of moisture. Everything in the design is purposeful, calculated to shave fractions of a degree of the ambient temperature. In certain regions, the towers are cylindrical rather than square, designed to catch swirling desert winds. In others, they feature directional scoops, permanently facing the prevailing summer breezes coming off the sea or mountains. Regardless of the specific shape, the underlying physics remain beautifully, monotonously consistent. The specific heat capacity of the Earth, the evaporative potential of water, and the pressure gradients of the wind. These are the invisible gears turning inside the medieval cooling machine. As we trace the path of the air one more time, allow your breathing to match its slow, steady descent. The wind catches the tower and falls into the dark, cool shaft. It glides over the subterranean water, growing heavier and colder. It flows smoothly into the room, bringing relief and tranquility. It gently lifts the warm air away, carrying it out into the vast, empty sky. It is a quiet, unending rhythm of pressure and release. The sun continues to beat down on the thick mud walls, but inside, nothing changes. It is simply dark, quiet, and cold. The geometry of the building has solved the problem of the day. There is nothing left to figure out, and nothing left to worry about. The system will continue to breathe for centuries, long after we have drifted to sleep. The steady, whistling draft is the only sound remaining in the shadowed halls. You can let go of the day, safe in the knowledge that the physics of the world are functioning exactly as they should. Rest now, surrounded by the cool, timeless engineering of the ancient past. Good night. Discover more history by watching the next video. We're eager to share more with you. You can't go wrong. All our videos are deeply detailed, dull while fascinating, and distinctly sleep-inducing.